Hello and welcome to another video lecture for machine design, ME372. I hope you're all doing well. I hope COVID hasn't influenced you, and I hope that you're healthy and your family is doing great. In this video lecture, we are going to review Castigliano's theorem on deflection, and then we are going to continue to work several example problems using Castigliano's equation. If you recall, we had this definition of Castigliano's theorem. And it says if an elastic system, so we know that the system must flex and stretch, is mounted so that rigid body displacements, so the system again can't just move as a rigid body, it can't be picked up and moved, it has to be stretched or pulled and displaced. Under certain concentrated loads, moments, distributed loads, and thermal strain, so almost any loading condition can be accounted for here. The displacement at the point of application of the force Fi and the direction of the force Fi is determined by this equation. So we have to have a force at the point and in the direction that we want to know the displacement. And if we do that, then the displacement is given by the partial of C, where C is the complementary energy with respect to the force at the point of interest. We came down here and we talked about how the complementary energy is the area above the load deflection curve, and it is called the complementary energy because it essentially completes this rectangle. The area under the curve is the well-known strain energy. Now we're going to take the advantage of being in the linear elastic region where C would be equal to U. When we do that, then we can write the displacement is equal to the partial of U, or the derivative of U with respect to Fi, and expanding that in terms of the well-known strain energy expressions, we get this big equation here. And we recall that this accounts for the four components of stress that we have recently talked about when doing combined loading stress problems. This first component is the axial load component. We have a normal force over an area. So this is like the force over area type of term. Then we have the transverse shear, the VQ over IT shear stress term. This K out here is a modifying factor, which is a correction factor based on the strain energy expression for VQ over IT. And it has specific constant values depending upon the cross-section of the beam. This next term down here is the flexural bending component. So M over I, this is the MC over I type of term. And then our last term is the TC over J type of term, where T is the torque. Let's look at using Castigliano's equation to solve this problem. It says find the maximum deflection in a simply supported beam of length L and with a uniformly distributed load of W, where W has units of newtons per meter, and we are to account for transverse shear. So here's our beam. It's of length L. We have a distributed load. Here are some initial observations. The maximum deflection will occur at the center of the beam. So when it says find the maximum deflection, we know that we need to find the deflection here at the center of the beam. The beam is symmetric, so we will look at half the beam and then multiply by 2. Make sure that when you look at beam symmetry, you multiply by 2 and don't divide by 2. And that's because there's twice the energy, not half the energy. There isn't a load in the direction at the point of interest in this case. We don't have a point force in the direction that we want to know the displacement. Distributed loads are not point loads. So we have to come here and add a point load in the center of the beam. So here's our solution. Set up a global coordinate system, and we can draw on X, Y, and Z if we would like to for the whole structure. Then we make sure there's a point load at the point and in the direction of the displacement. And in this case, there isn't one, so we apply a dummy load. We applied load Q in the middle of the beam. So here is load Q, and I often draw Q with a squiggle line so that I remember that it is the dummy load at the point of interest. And then we do simple statics to find the reactions and put our system in equilibrium. So I have to get my entire system in equilibrium, and I do that by coming here to this point and summing forces and summing moments. And using symmetry in this case, we know that this reaction force pushing up will be WL over 2, where WL will be the total load applied by my distributed load. And then we have Q over 2. We'll have half of the Q here, and we'll have half of the Q over here on this side. The next thing I do is determine the expressions that go into the integral equation used to compute the deflections into Castiglianos equation. And I determine those expressions by making a cut and summing moments and forces. So in this case, we're going to sum the forces and moments at the cut, and we're going to start at the left end of the beam and let the beam go to the right. So a free body diagram of that looks like this, where I have my WL over 2 plus Q over 2, and I have W out to this point. Now you note that this is just at some arbitrary distance X. I have not gone to the middle of the beam or past it. I have just gone some arbitrary distance X, and I have not even gone to the middle of the beam because you can't see the Q. So this is a region before the middle of the beam. And now what I'm going to do is sum the moments. And making counterclockwise positive, I have minus MA, because this moment's going this way, plus WL over 2 plus Q over 2, this force, times the lever arm, X. So summing moments at A, I get this expression, and solving for the moment at A, I get this equation here. Now I simply sum the forces, and I know that this force will be minus FA because it's pushing down, and I'll have a minus W times X, where the W times X is the force due to this distributed load, plus WL over 2 plus Q over 2. So here's summing forces. Now solving this expression for FA, I get this equation. And now I take my derivatives, and I take my derivatives with respect to Q. So I've taken the derivative with respect to Q. Doing that up here, I get X over 2. Doing that here, I get 1/2. Now I write out Castiglianos equation, and when analyzing a symmetric beam, you can analyze half the beam and then multiply the result by 2. Don't divide by 2 like we talked about. So doing that, Castiglianos full-blown equation is given here. Again, I don't have any torque terms, and I don't have any normal force terms. So my Castiglianos equation reduces to this expression here, where I have FA and the partial of FA and MA and the partial of MA, and I have computed those expressions or determined those expressions on the previous page. So I now substitute in those expressions here for Y, and I get Y total then is 2 times Y. So here's the 2, times all of these integrals. And at this point here, after we have substituted into the integral, I can now set Q equal to 0. Q is the dummy load, and it does not have a numerical value, and so at this point here, I can set it equal to 0. You need to make sure that you don't set Q equal to 0 up here, because if you set Q equal to 0 here, then when you went to take your derivatives with respect to Q, you wouldn't have any Q terms, and you'd get zeros. So I set my Q equal to 0, and I rewrite my equation, and now I can perform my integrals, and I get this expression, and this would be the expression that would represent the total displacement at the center of that simply supported beam. Now, one thing to note here is when we set up our initial equations, we could have gone from the other end of our beam. We could have started over here on the right end and integrated to the left. We would get the same answer. Similarly, up here when we did the cantilever beam problem here, we came from the free end and integrated this way. The only reason we did that is because all we had to deal with here was an applied load P. If I would have come on this end of the beam and made my cut in here and then integrated towards the right, I would have had to integrate a PL plus a P times X term, and my integral would have been a little more complex. But I would have got exactly the same answer. So when dealing with determining where to make your cut, it's easiest to start on the free end of a beam and work towards the fixed end. If your beam has boundary conditions on both ends, it doesn't matter which end you start on. It doesn't really matter which end you start on if your beam has a free end and a fixed end. It's just usually a little bit easier if you start at the free end. So hopefully this gives you a little bit of insight into determining how to make your cuts. In summary, if you have a free end, typically start at the free end and integrate the other way. If you have boundary conditions on both ends that are not free, then start at either end of the beam. It doesn't matter. So hopefully this example showed you how we handle the Q if we don't have a point load applied here, and then also how we can multiply the expression by 2 to get the total displacement, and then we can perform our integrations, and you can see here that this is left to be evaluated at L over 2. The thing that you would not want to do is evaluate this from 0 to L and also multiply by 2. That would be like double counting. So when we multiply this by 2, we integrate. Let's work another example. In this example, it says determine the maximum deflection in the beam shown. The beam is long and slender. So we look at this beam and we can see again that it's simply supported. We have two externally applied loads, each of magnitude F, and each applied at a distance A from their respective ends. The problem statement says the beam is long and slender. That implies that the transverse shear stress, VQ over IT, is not significant. And so we will neglect the transverse shear stress term in our Castiglianos expression. The maximum deflection will occur again at the center of the beam. So we need to apply a dummy load at the center of the beam because there's not a point force at the center in the direction we want to know the displacement. Again, we will take advantage of the beams being symmetric, and we will only look at half the beam and then multiply by 2. So to begin with, we will set a global coordinate system, and we'll have a horizontal x-axis. We will then apply the dummy load at the point we want to know the deflection and in the direction. The dummy load here is represented by the dashed line to distinguish it from the externally applied loads F and F here. We now need to put the entire system in equilibrium and determine the reaction forces and moments. For a simply supported beam, we know that the reaction moments at the ends must be 0. So through summation of forces and summation of moments, we can determine that this reaction is F plus Q over 2, and this reaction is F plus Q over 2. So now we are going to determine the integral terms that are required in our Castiglianos expression. Now we note up here that we have this region from 0 out to A, where there is only F plus Q over 2. Then in a shear diagram, we note that this force would change that. And so we have a region that is different with a different shear force in the region between A and L over 2. So we have to actually break this problem up into 2 integral steps. We'll have the first step from 0 to A. And so I will come down here and define my positive coordinate system going to the right as X. I'll list on the force that is applied, F plus Q over 2. And I will put the assumed direction of my moment at A. And we know that this will counteract the F plus Q over 2 here. So summing forces at the cut, it must equal 0. This results in MA minus F plus Q over 2 times X, and that equals 0. So solving for MA, we get F plus Q over 2X. And we can take the derivative of MA with respect to Q and get X over 2. Now we need to look at the region from A to L over 2. So to do that, we draw a new free body diagram. We keep our same origin, and we redraw this end of the beam, starting here at our fixed x-axis. And we go out now to the region between A and L over 2. And you can see that we have drawn on here the force F, and we have our reaction force down here, F plus Q over 2. So now again, I sum moments at the cut, and it must equal 0. I'm going to have the moment at A minus F plus Q over 2 times by X plus F times X minus A. So this force here acts at X minus A from the cut end. The distance X would get me out to the end, and then I subtract the distance A, which gets me to the location of the force F. So I can solve for my moment here at A now, and I can take the derivative with respect to Q, and I'll get X over 2. And now I set up my 2 integrals and multiply them by 2 because I have only looked at half of the beam. So again, my first integral will go from 0 to A, and here is the expression that I would have. This should be a big EI. And then I integrate from A to L over 2, and then here's the moment that I'm integrating. Here's the derivative of the moment with respect to Q, and so here's the expression from A to L over 2. Now I can set Q equal to 0 and rewrite the expression, and then I can perform these integrations, and I end up with this expression for the displacement in the middle of that simply supported beam. So again, the key result here, or the key demonstration principle, is that whenever you have an external force applied, or a change in geometry, or an external moment applied, you need to write a new moment expression. So here we had one moment expression from 0 to A, and then we had a force change, so we need a new moment expression that will take us from A to L over 2. We have now used Castigliano's equation to solve for the displacement in statically determinate beams. We are now going to look at an example where we can compute the displacement in a statically indeterminate structure. Castigliano's equation is a single equation, and so there can only be a single unknown. And in the previous examples, that unknown has been the displacement. However, if the displacement at a particular location is known, the unknown that is solved for can be the force. And that's what we'll do in this example below. So in this example, it says determine the displacement at the center of the beam system shown. We recognize this as a statically indeterminate structure because we see here we're cantilevered on this end and we have a roller here. If I were to remove this roller, this beam could still stand up. I could also remove the moment part of this reaction and just have a vertical reaction, and I would have a simply supported beam and the beam could stand up. So this is a statically indeterminate structure because I have too many reactions for the equations that I have to solve for them. So in order to determine the displacement at the center of the beam, we need to know the reaction loads at the ends of the beam. And since we can't use statics to do that, we're going to use Castigliano's equation, but we're going to use it in a two-step process. First, we will let the displacement be 0 at the roller, and we'll solve for the force that makes this true. Then once we have that force, we can treat it as an applied load, and then we can solve for the displacement in the center of the beam. So to begin with, we'll start by drawing a free body diagram of our structure as shown here. RB is the reaction due to the roller, P is the applied load, RA and MA here are the reaction moment and force at the cantilevered end. So we see that in order to apply Castigliano's equation for this point here, we're going to have two integrals because we will have a change in our shear force equation and our moment equation here in the center. Again, in this problem, we are going to assume the beam is long and slender and only concern ourselves with the moment component of displacement. So coming down here for the region between 0 and L over 2, I define my coordinate system here as x. I have my reaction B, and now I have my moment at A, where this moment is the moment at the cut. So summing moments at the cut, I have MA minus RBX equals 0. Then I look at the region from L over 2 to L. Here's my reaction at the roller, here's my applied force P, and here's my cut edge. So I sum moments at the cut, I get moment at A plus P times x minus L over 2, where x minus L over 2 is the distance from P to the cut edge. The distance x gets me clear out to the cut edge, and then I subtract L over 2, which is this distance here, between P and RB, which leaves me with the distance between the cut edge and the force P. And then I have minus RBX equals 0. I can now rearrange these equations and take the derivatives. And note that I take the derivative with respect to RB. So I take the moment at A, which is RBX, and the derivative with respect to RB, which would be X. Here I do the same thing for moment A in the L over 2 to L region, and I take the derivative. So now substituting these quantities into Castigliano's equation gives the displacement is equal to 0, which is equal to 0 to L over 2 of RBX over EI x dx plus L over 2 to L times this moment component. And there should be a dx here. Now what I need to do is solve these expressions here for RB. And doing that, I solve for RB, and I get RB is 5p over 16. Now, when solving the second part of this problem, which will be to look at the force P in the middle of the beam, RB is treated as a constant force and not a function of P. So we will not take derivatives with respect to this RB because this is a constant. So we're going to treat the beam as a cantilever now with two loads. And don't put the constraint load in as a function of P until the derivatives have been taken. So we have RB acting up here and we have P pushing down. And now again I will have two integral expressions. I'll have the integral expression from 0 to L over 2 and L over 2 to L. Here are these quantities for the region from 0 to L over 2. This is my free body diagram, and I sum moments about A. And we note that we leave RB in as the quantity RB, and we take the derivative of MA with respect to P, and we get 0. And so this part of the problem is not included in Castigliano's equation to solve for the displacement. Now we look at the region from L over 2 to L. And here we have our reaction at the roller, we have our applied load P, and now my cut is between L over 2 and L. I come down and I sum moments at the cut, and I get the moment at A plus X minus P times X minus L over 2 minus RBX. And I come down here and I solve for MA, and I take the derivative with respect to P. Again, I don't have the P in the RB because I treat that RB as an independent constant force. I take the moment, I get this expression, and now I come down and I put all of that into Castigliano's equation, and the only term that I'll have in Castigliano's equation is the integral from L over 2 to L, my moment expression, my moment arm, dx. And I can integrate this now to solve for the deflection in the center of the beam. So again, in statically indeterminate structures, what we did was we knew the displacement at the point of interest, and we solved for the force. And then we treat that force as a constant. So RB equals 5p over 16 is now treated as a constant force, not a function of p that gets taken derivatives of. Then we solve for Castigliano's at the center of the beam, and we computed the displacement y. So hopefully this gives you a good example of how to use Castigliano's equation to solve. The last example that we are going to work using Castigliano's equation is to solve a structure that is built out of two beams. These are often referred to as built-up structures. We can see the built-up structure shown here consists of what we call a torsion arm. So here, fixed at the wall, we have a rod that is cantilevered, and then at the end of this rod we have a bar that comes out at a 90-degree angle with an end force F applied at the end of that bar. We can see that we have a distributed load along the circular cantilevered rod. The bar here only has a force applied at the free end. The problem statement says compute the deflection at point A in the torsion arm that has distributed load W on member 1 and a point force on the free end of member 2. It says neglect transverse shear in all members. So when we look at this, observations that we see that the torsion arm consists of two beams. So M in Castigliano's equation is now going to be equal to 2, whereas before in the examples it has simply been equal to 1. So we will need to separate and look at each of these beams individually. There isn't a point load in the correct direction at point A. The problem statement says to determine the deflection here at point A. And we don't have a point load there, so we are going to need to add a dummy load. The only component to cause deflection at point A in member 2 is bending. So if we look at just this member here, we think about Castigliano's equation and the four terms in Castigliano's equation, the only term that is going to apply in this member is bending, the M over I term. When we look at member 1, we can see that the deflection at A is going to be affected by the vertical deflection at the end of this. So we will have bending here in member 1. But also, if member 1 is twisted, it will rotate point A down. So we will also need to account for any torque in member 1, because as member 1 twists, point A would rotate down. So we'll have bending and torsion in member 1. The solution steps will be as follows. First, we'll apply a global coordinate system, X, Y, and Z. And when we're dealing with built-up structures, the definition of a global coordinate system is a lot more important than it is when we're dealing with a single beam that is essentially a 2D problem. So here I've defined X as positive coming along the rod, Y positive going in the vertical direction, and Z coming out of the page. Now we make sure there is a point force at the point and in the direction of the desired displacement. So in this problem we add dummy load Q, and here it is shown with a squiggle line. Now what we're going to do is we're going to break the member into two individual beams. We'll draw the free body diagrams for each beam, and we'll determine the integral expressions for each beam, and then we will add them together. So note that all applied loads, not reaction loads, must be transferred to each member. So what that means is when we analyze this rod, we need to make sure that all of these applied loads here are transferred to the rod. So looking at part 1, which is the rod, we can see that the rod is cantilevered. It has a distributed load, and then it will have an end load Q plus F, and it will have a torque of Q times L over 2 plus F times L. So this is the applied torque, and this is the correct direction for the applied torque. So these forces and moments here are as they are applied to the structure. So we treat these as applied loads and we apply them in the directions that the applied loads are applied. These are not treated as reaction forces. They're applied forces and moments. So given these applied loads, we will now make a cut in the beam at a distance x, and we will determine the reaction forces and moments. So I come and I sum moments at the cut. I have the moment at A at the cut minus W times X, which gives me the force, times X over 2, which is the average distance at which the force acts away from the cut. Then I have minus Q plus F, which is this force, times the distance X, all equals 0. Then I sum the torques, and I have the torque at A minus Q times L over 2 minus FL equals 0. And so I have the torque at A. Now I take the derivatives for the part 1 terms, and I take the derivatives with respect to Q. So taking those derivatives, I get these expressions shown here. Now, part 1 continued, I take and I have a moment component and I have a torque component. So I integrate from 0 to R, which is the length of the rod, and I have my moment component and my torque component. And now I let Q go to 0, and that results in Y1 being this expression here. I now take part 2, and part 2 is the bar. And acting on the bar, I have the force F, and I have the force Q. And so I'm going to have two parts to integrate. I'll have to integrate from 0 to L over 2 in this region, and then from L over 2 to L. So in the part from 0 to L over 2, this is my free body diagram. All I have is the force, and then I solve for the moment at A. And I note that there's no Q in this expression. And so there will be no contribution to the overall deflection due to this region here. I now look at the region from L over 2 to L in the bar. And so my cut now is in this region out here, L over 2 to L. And I sum the moments. I get the moment at A. Then I have Q times this distance here, which is X, gets me to here, minus L over 2, which takes this part off and leaves me with this distance here, minus F times X, and I have my moment at A. I can then solve for the moment at A and take the derivative with respect to Q. My Y2 expression, combining terms, then is the integral from L over 2 to L, and the rest of the expression is given here. I now take those expressions, and to get the total displacement, I sum the contributions from the first member and the second member. And so this becomes Y total, where I have the bending from part 1, the torsion from part 1, and then the bending from part 2. Now we check to make sure that this answer makes sense, and we just explained, and through the process explained why it does. So hopefully you can now see how to use Castiglianos effectively for built-up structures. You will be expected to be able to do built-up structures on an exam and on quizzes. So make sure that you get built-up structures understood. You'll also be expected to do statically indeterminate structures. So if you have questions on these problems and these concepts, please get with me and get with Tyson or Devin for TA hours. and we will get you so that you're able to understand this material. Don't let it seem too hard. It's a little challenging until you see it, and once you see it, it's pretty straightforward. So if you're having questions with it or challenges,